Everyone, this is Mrs. Lindsay Pereira. Today we are talking about perimeter and area in a coordinate plane. But before we do this, we actually need to talk about polygons. All right, definition of a polygon is a plane figure with the following properties. 1, a closed figure, so again, no openings, a closed figure formed by 3 or more line segments, and we call those sides. 2, the sides intersect at points what we call vertices. Okay. 3, the angle between the two sides is called an interior angle or a vertex angle, and we will almost always refer to it as an interior angle, but we do use vertex as well. And 4, and an important little concept part right here, you name a polygon by listing its vertices consecutively. Okay, so you can't jump around with that, and I'll talk about a couple examples with those. It doesn't matter which direction you go though, if it's clockwise or counterclockwise, but you pick one vertice and walk all the way around the polygon in one direction until you get back to the original vertice. Okay, so it's not necessarily alphabetical. It seems like it is sometimes, but it's just starting at one vertice, going around until you get to the original vertice again. Okay, so here are some examples of polygons on the top and some examples that are not polygons. So let's take a look at the ones that are not polygons. So a few different things here. We have some of them that are not closed. That would be this first one here right next to the heading, and then we have another one here, and I would even say this one's pretty close. Okay, not closed. We got a little portion right here. Then we have ones, again, they have to be formed by sides. So a circle cannot be a polygon. We don't actually have sides on that. Okay. And then they cannot be, this one would also classify as not sides there. And then our other ones would be they can't intersect. The lines cannot intersect. Okay. So those are examples of not polygons. We can also describe our polygons by talking about convex and concave. Sometimes you'll see this as non-convex. They'll write it that way. But what is convex? First of all, convex is a polygon in which each interior angle has a measure less than 180. So if I'm looking at all of these angles here, okay, none of them are greater than 180. They're all less than 180. But you can see on the concave ones, the way I like to think about it, I kind of highlighted it here, it caves in. This angle was definitely greater than 180 degrees. We don't know what it is, but we know it's bigger than 180 degrees because it goes past the straight line. Okay, that is concave. All right, so these figures are convex, but realize not all of them are polygons. Not a polygon, and not a polygon, okay? But they are all convex, okay? These figures are concave, so again, you have that one angle that is larger than 180 degrees, and again, they're not all polygons. Not polygons, but they are concave, okay? And we also have names for these polygons. Okay, so this is listed in your book, number of sides versus the name here. One of them is not in the book that you need to know, but you do need to know these. Some of them you probably already know. Triangle has 3 sides. Pentagon has 5 sides. Some of them you might not know. 9 sides is a nonagon, that type of thing. But make sure you do know this list. Anything that's not on this list. Now there are some other names for some of these polygons, but this is what I'm requiring you to know, what's in their textbook. Besides the pentadecagon, I would like you to know that, but it's not in the book. If it's anything else, for example, if it has 20 sides, it's called a 20gon. Okay, 30 is 30gon. 142 is 142gon. That type of thing. So again, if it's not on this list, it's the number gon. That's how you would name that. Okay, so again, make sure you know this list. All right, so let's do a couple examples here. So classify each polygon by the number of sides, and then tell whether it's convex or concave. So this one has 1, 2, 3, 4, 5 sides, so it's a pentagon. And nothing caves in. All these interior angles are less than 180, so this would be what we call convex. And if we go over to B, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is what we call a dodecagon. 12 sides. And again, this kind of caves in a couple different spots. So these angles here are greater than 180 degrees. So that would be concave. Okay. All right. Moving on to our next example here. So this is on the coordinate plane, okay? So we want to find the perimeter of A, B, C, D, E, F. So started at one vertex and named it by going clockwise all the way around. You don't have to put it in alphabetical order starting with what comes first. I could have started with, for example, E, and I could have gone the other direction. So E, and then again, I go all the way around. In this one, I went counterclockwise. So I'd go E, D, C, B, A, F until I get back to E. So again, that names this polygon. I don't have to name it in several different ways. I would say a lot of people like to try to put it in alphabetical order. But again, it doesn't have to be. Okay, so that's how you name a polygon. Okay. So now that we talked about that, let's actually find the perimeter of this. So we're kind of fortunate because we have a lot of vertical and horizontal lines here. So we can literally just count from F to A to find the distance there. So from -2 to 0, that would give me a distance of 2. Here's a vertical line. So again, now I'm looking at my Y's. So again, I see that's a distance of 2 from my Y value of 2 to 4. We'll talk about AB and ED in a second. So here we have another one, which would be a distance of 2, and then a horizontal line here, which would be a distance of 2. So we have part of the perimeter, but we definitely need to find, okay, what's the distance here of AB? What's the distance here of ED? So for that, we're going to use the distance formula. So the distance of AB, okay, so let me write first down the distance formula. Again, subtract your x's, square it, plus subtract your y's, and square it. Okay. So here we get our x's. So 0 minus 2. Doesn't matter which order I go in, but if I choose this x first and subtract 2, then I have to choose this y first, which is 4. The one that matches up with the x I chose first, and then subtract 0. So I get this to be -2 squared, which is 4. 4 squared, which is 16. Square root of 20. And we're going to reduce that. 4 and 5 goes into that, so it'd be 2 root 5. Okay. I would like you to pause the video and find the distance of ED. Push play when you're ready to check your work. All right, so it should be also 2 root 5. So perimeter of any object is add up all the sides. So here I have 2, 4, 6, 8 plus 2 root 5 and 2 root 5, so that would be 5 root 5. Now this is an exact form. Please follow directions. If I say exact form, I would want a simplified radical. If I say round, then I would go ahead and plug this into my calculator, which I'm pulling up right now. If I don't specify, I will take either form. Okay, so in this case here, let me go ahead and clear this out. So it'd be 8 plus 4 root 5. So that would be approximately 16.94. So in this case, I don't specify in the direction, so I would actually take either answer here. But again, exact form, no rounding. If I ask you to round, just follow the decimal places. Okay, so next, let's find the area of triangle EFA. Okay, well, since we know this is a horizontal and a vertical line, that's our right angle. Area of a triangle, 1/2 base times height. So my base and my height are both going to be 2. So that area would be 2 units squared. Okay. And then we're going to find the area of triangle BDC. Same idea, horizontal and vertical. So these happen to be the exact same that we did up here. So that's also going to be 2 units squared. Quick little note what I was talking about here with base and height. If I'm given a parallelogram, usually we put base here, and then we would talk about the height. But any side can be the base. I can make this side be the base. I just then need to draw a perpendicular to that base, and that's the height. So this could be the base and the height that go together. This would be a second base and the second height that would go together. It works the same with triangles too. So even though I had a right triangle in our last problem there, I could say this is our base and this is our height. But I also could call this side a base, and the corresponding height would be the perpendicular to that. So the area could be figured with what's in blue, or could be figured with what's in green. Just remember, the relationship between the base and the height is a perpendicular. Okay, and we'll get into that more as we get into area later on in the semester. Okay. All right, one last example here. Now we have this diagram. We're trying to find the area of the rectangle. So area of a rectangle is base times height. So here's our rectangle that is dotted. So this again is nice because this is actually in terms of horizontal and vertical lines. So if I go from 2, and I know this point here has to be 10, so I know that distance would be 8. Okay, so now if I'm going this direction, I know I have a y value of 3, and this has to be at 8 for my y value, so that would be 5 right there. Okay, so we can actually fill in these ordered pairs. So in this case here, to find our area of our rectangle, we would get that to be 40 units squared. Okay, so we're probably going to want to fill in these so we can find the area of triangle ABC. Well, sometimes it's easier to find the areas of other things and subtract them. So in this case, it might actually be easier to take the area of the rectangle and then subtract off all these triangles. So let me just label these triangles. 1, 2, 3. So area 1 minus area 2 minus area 3. So I'm going to subtract off all these triangles from our rectangle, which we already found to be 40. So again, if this had to be 8, we also knew this y value had to be 2, right? So this would be 5, and then this distance here would be 2. So that would give us 1/2, 5 times 2, so that's 10, so half of that would be 5. And same sort of idea here. Well, this distance here goes from 4 to 10, so this has to be 6, because again, I know this value here has to be 10, and then this y value still has to be the same as this 8 here. So now I know this would be a distance of 3, so 1/2, 6 times 3, so a half of 18, that's going to be 9. Same sort of idea here. So again, this has to have a y value of 3. So that would give us 2 here. So 1/2, 8 times 2, which is 16. So half of that is 8. And then we subtract, and we get that to be 18 units squared. Again, definitely a lot easier to do it this way when we're finding this because we have no vertical and horizontal lines, so it doesn't automatically give us our base and height. You can use distance formula to find some of those things, but this is by far the easiest way. Okay? All right, and then so this concludes our notes for section 1-4.